All right, continuing with our discussion on acids and bases, let's look at slide 11. And you'll notice that we have a table of our acid dissociation constants, our Kas, for a variety of different acids. Okay, most of the time you're going to be looking up your Ka for acids or your Kb if we're looking at bases. We'll talk about those later. You're going to look those up in a table. All right, now notice that we have them tabulated from small Ka all the way up to some big Kas. As we go from small Ka to big Ka, we are increasing in our acid strength, right? Because we're getting more and more dissociation as we go along, right? Now, on slide 12, I want to talk a little bit about a special acid-base system, all right? So we have water, which can act as either an acid or a base. So when it acts as a base, it's going to accept a proton. So for example, when we had HCl and water, notice that our H2O picked up the proton from the HCl and became H3O plus, and we had Cl minus in solution. Okay, so in this case, H2O accepted a proton and acted as a base. It can also act as an acid, in which case it will donate a proton. All right, in the case where we have ammonia, NH3, and we've added water, notice that it forms an equilibrium where we form NH4 plus, and the H2O gives up one of its protons to the NH3 to become OH minus. Okay, so notice that water can either act as an acid or a base. When it does this, right, any substance that acts as either an acid or a base is called amphoteric. All right, so that's one of those cool properties of water. Now, moving on to slide 13. All right, since water can act as either an acid or a base, what's going to happen if we have just a system of water? All right, like we have just a beaker of water or a glass of water. Well, we're going to end up getting an equilibrium between the standard forms of water, right, H2O, and the acid-base forms, right? We have H3O and OH minus, right? So you can imagine that if we put one water molecule with another, one of them could act as a base, right, and accept a proton, and the other one could act as an acid and give up a proton, okay? So this special type of dissociation forms for water, right? And so we end up with a special dissociation constant, right? Water's not really, I mean, it sort of is, right? Sort of dissociating, but it's forming this equilibrium. So it gets a special dissociation constant, which we call Kw, okay? Now, recalling that we don't include H2O, right, our concentration of H2O in our equilibrium constants, our Kw, our water dissociation constant, is going to be our products over our reactants, but since our reactants are both water, we're just going to have our products over 1. So we're going to have H3O plus to the first power using its stoichiometric coefficient, and our OH minus to the first power. Right now, as I said before, right, we could end up getting rid of one of the waters, right, for a non-participating species, right, this one, or I should say this one became the H3O plus, right? You could imagine that really it could also be written as H2O forms an equilibrium with H plus and OH minus, right? But in that case, right, you would end up with H plus to the first or OH minus to the first. Those two are equivalent forms. You could write it either way, right? Now, at 25 degrees C in pure water, our concentration of H plus at equilibrium is going to equal our concentration of OH minus at equilibrium. And they happen to be 1.0 times 10 to the negative 7th molar, okay? That means that if we plug those into our Kw expression, right, we're going to get 1.70 times 10 to the negative 7th for the first one. We'll have 1.70 times 10 to the negative 7th for the second one. And so we'll get that quantity squared, which will give us a Kw equal to 1.0 times 10 to the negative 14, right? That is going to be the value for your water dissociation constant, right? I'm going to expect you guys to have that memorized, okay? So make sure you keep a note of that. It's going to be really useful as we do our acid-base chemistry. All right, now, a couple things that I wanted to point out is that for neutral water, right, water that doesn't have anything in it, right, pure water, right, we had that our concentration of H plus was equal to our concentration of OH minus, right? Now, if we have an acidic solution, right? That means that we're going to have more H plus in solution than we do OH minus, right? It's going to be more acidic than it is basic. We often associate H plus with our acid, right? And OH minus with our base. So if it's more acidic, we'll have H plus concentration greater than OH minus concentration at equilibrium, okay? The opposite is true for a basic solution, where we will have our concentration of H plus that is less than our concentration of OH minus, okay? Now, one thing that I did want to point out is that Kw at 25 degrees C is always equal to that. So even though we may be changing our concentration of H plus and OH minus, okay, as we increase the concentration of OH, or as we increase the concentration of H plus, as this goes up, our concentration of OH minus will have to go down. So if H plus goes up, OH minus has to go down to make sure that we have our equilibrium constant, okay? That's why this is called a constant, because that number stays the same, but these numbers can go up and down depending on our equilibrium position, right? Remember, we could have an infinite number of equilibrium positions, which are an infinite number of different concentration combinations to give us our Kw equals 1.0 times 10 to the negative 14. Okay? Now, our next topic is going to be really, really important for our acid-base chemistry. Okay? We are now ready to begin talking about pH. Whew. Didn't work out. Okay, so if we look at slide 14, we're going to talk about our pH, okay, which is basically what we use to quantify the acidity or the basicity. Okay, so let's say since the concentration of H plus is often very small, okay, we need a way to define our pH, and so we define pH as pH equal to the negative log base 10 of the concentration of H plus. Okay, this will be an incredibly useful formula for you guys. Okay, now pH, that P stands for the power of H plus, okay? And I'll talk to you a little bit more about what that means in a second, okay? Now, if we have neutral water, so for neutral water, right, we said that our concentration of H plus was equal to 1.0 times 10 to the negative 7th molar, right? So if I wanted to calculate my pH of neutral water, it's going to equal negative log base 10 of 1.0 times 10 to the negative 7th molar, okay, which is going to equal 7.00. Okay, so my pH of neutral water happens to be 7. All right? Now, you're probably going to want to know how to get our significant figures. Okay? So, for the significant figures, okay, the number of sig figs in the log is equal to the number of decimal places in the answer or in the result that you get. All right? So that means that say you have the log base 10 of 1.0, okay? You have two significant figures, right? We have two significant figures in our log, okay? Oh, I'm sorry, 1.0 times 10 to the negative 3, okay? We still have two significant figures, all right? And that's equal to two decimal places in our answer. So this would be equal to 3.000, blah, 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 right? But we're going to cut it off such that it says 3.00 with two decimal places. Okay, so your number of sig figs in the log is going to equal your number of decimal places in your answer. Okay, so another example of that would be, let's say we took the log base 10 of 1.00 times 10 to the negative third. That's going to equal 3 right? That's going to equal 3.0000000 and so on. But since we had three significant figures, we're going to have three decimal places. So we go 1, 2, 3. That means that all of this other stuff goes away, and we're left with 3.000 as our answer because we need three decimal places. All right? Now, that covers the introduction to that part. Now I wanted to talk to you a little bit about that power of H. Okay? Now, pH, as I said, means the power of H. Okay? And it comes from a German word, potens. Okay? You don't need to know, that's just a fun fact. Okay? So it literally means power of H plus. Okay? So if we apply it to other concepts in chemistry, right, we could get our POH, right, which would be the power of H, or power of OH. Power of OH minus. Okay, so if we wanted to calculate our power of OH, our POH, that would be equal to the negative log base 10 of our concentration in OH minus. Okay, so that's another one that's pretty useful. All right, we could also apply it to our power of our equilibrium constant, right? We could say something like our pKa, or our power of Ka. Well, that's going to be equal to the negative log base 10 of our equilibrium constant, or our acid dissociation constant. Okay, so any type of thing that you put after the power is going to be the negative log base 10 of whatever you put in. Okay, so for example, if we add the pH, right, the power of our H plus, to our power of OH minus, okay, well, we know that that's going to be equal to 14.00, right? Because if we took the power of H, right, our pH, negative log base 10 of 1.0 times 10 to the negative 7th, right, we found that that was equal to 7.00, right? And we know the concentration for the OH is the same, right? So if we wanted to get our POH, that's the negative log base 10 of 1.0 times 10 to the negative 7. That's also equal to 7, right? So if we added those two together, we would get 14, okay? Now, we also know that if we took our concentration of OH minus and multiplied that by our concentration of H plus, right, that was equal to our Ka, or sorry, that was equal to our Kw, right? Yes? So that means that we also know that this is equal to 1.0 times 10 to the 14th, right? Or negative 14th. And then we know also that Ka times Kw is equal to Kw. Or sorry, Ka times Kb is equal to Kw. Okay? So this will be another equation that you'll want to know. All right? And we'll end up using that pretty soon, I would think, once we get into some examples. But I wanted to make sure that I covered all these concepts so that way we could sort of walk through the examples with some ease. All right? Now, for every pH change, right, so pH is a log scale, okay? And what that means is that it is based, in this case, it's a log base 10, which means it's based on powers of 10, okay? So that means that pH, if your pH changes by 1, okay, then that means that we have a 10 times change in the concentration of H+. Okay? So let's say that we had a pH equal to 3, okay? That means that a pH of 3 is 10 times the concentration of H+ as a pH equal to 4. Okay? So if we change a pH of 2, right? So we have 2, that would mean a pH of 2 is 100 times more concentrated than a pH of 4. Okay? So for every integer that you change your pH, okay, down, it becomes 10 times stronger of a concentration of H+. All right? So pH less than 7 is going to be acidic. Okay, because notice as we dropped our pH, we became more concentrated in H+. All right, a pH greater than 7 is going to be basic. Okay, because as we went up in pH, our concentration went down. All right, and a pH equal to 7 was neutral. Okay. Now, to give you an idea of how this sort of works, I wanted to point out a couple of things you might want to notice. We have on slide 16 a couple of charts, okay? And notice that pH decreases as our concentration in H+ increases, right? So as we increase H+, we become more acidic, and as we become more acidic, our pH goes down, okay? Right, because we go lower and lower below 7, okay? That's the first thing I want to point out. The second thing is pH increases as our pOH decreases, okay? And the third thing is, right, so basically, you can think about it, right? Our pH is going to go up, okay, so we're going to become more and more basic, which is going to have the opposite effect as pH, since we're talking about pOH, all right? The third thing I wanted to point out is that the pH scale ranges from 0 to 7 to 14, where at 0, from 0 to 7, we are acidic, right? And you become more acidic going that way. We are neutral at 7, all right? And then we are basic above 7 up to 14. All right? This is going to be your key takeaway. All right? I would say, if I were to summarize some of the points in this section, what I would say is you need to know that your pH is equal to the negative log base 10 of your concentration in H+. You need to know your pOH is equal to the negative log base 10 of your concentration in OH minus, right? You need to know your definition for pKa. You need to know that Ka times Kb is equal to Kw. Ka times Kb is equal to Kw, which is equal to 10 or 1.0 times 10 to the negative 14. Okay, and each of those is going to be different depending on what acid or base you're looking at. Okay, so those are some big key takeaways. All right, and also remember that as you become more acidic, your pH is going to go down and your concentration of H+ is going to go up. And as you become more basic, your pH, or your pH is, as your pH goes up, that means that your concentration is going to go down for your H+, but your concentration of OH is going to go up. Okay, so let's write that. As concentration in H+ increases, that means your concentration in OH minus decreases. So if your concentration in H+ goes up, then that means that your pH goes down. All right. And your pOH goes up. Okay. So keep that in mind as you go through. All right. I think we probably covered enough terminology. I think you guys are probably ready for some examples. Okay. So, man, this board is hard to clean. Okay, so let's erase that. I've got a nice full board to work with for you guys. All right. So, how are we going to calculate our pH in a solution, right? First thing that we're going to ask when calculating pH, when we calculate pH, our very first question that we need to ask ourselves is it a strong acid? Okay? If yes, then we're going to write our dissociation reaction. Okay? Then we're going to convert moles of a compound into molarity, right? Or into moles of H+ in solution. Okay? Once we've done that, then for our fourth step, we're going to calculate our pH equals negative log base 10 of our concentration in H+. Okay, so working through an example on slide 17. Also, I want to know, are the steps helpful for you guys? Please let me know in our discussion or send me an email, because that will be helpful for me to know whether or not this is good for you guys, because it does take up a fair amount of time, but I want to make sure that it works for you guys. Okay, so feel free to reach out to me. Working through the example on slide 17. Okay, we have for 1.0 molar HCl. Our first question is it a strong acid? And the answer is yes. Remember that I did ask you guys to memorize your acid and base, or sorry, your strong acid and weak acid table earlier this week. Okay, so we have our strong acid. So that means that we can move on to step 2. Step 2 was to write our dissociation reaction, which is HCl dissociating, right? Since it's a strong acid, we'll have a big arrow going to the right and a little one to the left. And we will have H plus Cl minus, right, because it wants to be dissociated. All right, then as step 3, we need to convert moles of HCl to moles of H plus, okay? And I would say we should probably just convert our molarity to molarity, because we're going to need our molarity to plug into our pH equation, right? So what we need now is we're going to take, we know that we have 1.0 moles of H plus per 1 liter of solution, right? That's our molarity of, or sorry, 1 mole of HCl per liter. And then we know that for every 1 mole of HCl, we have 1 mole of H plus, right? Every mole of HCl is going to give us 1 mole of H plus, okay? So that means that these are going to cancel, and we're going to have a mole of H plus over our liter, right? So we do the math, and we end up getting that this is 1.0 molar H plus, okay, as our concentration of H plus. Right? Our next step, step 4, is to use our equation, right, which was pH is equal to the negative log base 10 of our concentration in H plus, right? So that's going to be the negative log base 10 of 1.0, right? We have 1.0 keeping our sig figs. We have 2 here, so we will have 3 outside, right? So this will give us 0.00, right? We have 2 decimal places outside, and that should make sense because it is a strong acid, so it will give us a very, very, very low pH, right? So that's our pH. Let's do another example on slide 18. All right, for this one, we have 0.327 molar nitric acid, which is HNO3. All right, our very first question is it a strong acid? And the answer is yes. Okay. The second one that we do, since it's a strong acid, is we write down our reaction, which was HNO3. It's dissociating, right? We need a dissociation reaction. So it's going to go to NO3 minus plus H plus, right? Again, we're going to have a strong arrow going to the right because it is mostly dissociating for a strong acid. Step 3, we need to convert molarity of our acid into our concentration of H plus. So what we are going to do is we've got 0.327 molar HNO3 per 1 liter of solution. And then we know that for every 1 mole of HNO3, how many protons is it capable of giving up? 1. So we're going to get 1 mole of H plus. All right. So that math is pretty simple. That's going to give us a concentration of H plus that is equal to 0.327 molar. All right. That makes our pH for step 4 equal to the negative log of our concentration of H plus equal to the negative log base 10 of 0.327 molar, which is equal to 0.485. All right, it is a strong acid. It's going to have a value that's close to 0 for your pH. Okay, something very important to keep in mind. All right, now let's say that we wanted to do another example. All right, but I want to expand this next example to cover several different concepts. Right, so far we've only calculated our pH. All right, how are we on time? Let's do that example in our next video since we're out of time for this one. I'll see you in a